Continuing with Chapter 5, there's a few different ways to calculate probabilities. We're going to talk about empirical and classical. This empirical is not the same as empirical from Chapter 3. This is a different method. So the empirical method is based on experimentation. So you go out, you run an experiment, and you gather your data. So to get the probability of your event, you just count up the total desirable outcomes. So if you were flipping a coin and you wanted to count up the number of heads, you'd count up the total number of heads you got out of the total number of trials. So if I ran the experiment 100 times, I'd divide by 100. If I ran the experiment 200 times, I'd divide by 200. So however many times I ran the experiment would be my total number of trials. And so the total number of desirable outcomes we call the frequency of the event, how frequently did what we were trying to get occur, divided by the number of trials. And you'll see that same formula on your formula page. If you turn to page 2, the top half of page 2 is all Chapter 5, and the first bullet there is the empirical probability. So the frequency of the event divided by the number of trials for the experiment. So empirical method is from an experiment. We're going to actually go out, run an experiment, and gather the data. So we do this based on data. So it's based on data given to us. So every time we run the experiment, we might get different results. So if I flip a coin 10 times, the number of heads I get the first 10 flips might be different than if I decide to flip it 10 more times. I'll get a different number of heads. So it's based on data and it's constantly changing. So the empirical method comes up with different results every time. And hopefully over time you get pretty reliable results. So here's a quick example of the empirical method. Talking about a casino manager. He wants to approximate the probability of rolling a sum of 7 using a pair of dice. This is for a casino game called Craps, and I don't know much about it, but I do know that the sum of 7, everyone loses their money and the casino wins all the money. So the casino manager wants to know how likely is it to get a sum of 7 using a pair of dice. So if you have 2 dice and you roll them both at the same time, you're adding up the 2 outcomes showing. So we can add it a bunch of different ways. You can get 10, you can get 4, all kinds of different things. There's 5, there's 4 again. So all kinds of different outcomes. And he's focusing on how many different times will it land and give me a sum of 7. Sum of 7 is when, again, all the players lose all their money and the casino wins all the money. So he rolls his dice and rolls his dice, and he counts up how many times the sum of 7 appears. So it says he rolls the pair of dice 100 times and records 15 times a sum of 7 occurs. So he concludes, using the empirical method based on his experiment, that there is a 0.15 or 15% chance of rolling a sum of 7 with a pair of dice. So he got 15 total outcomes that he wanted out of 100 total trials, which gave him that empirical probability of 0.15. And I want you to just think for a minute, how accurate do you think that experiment is? Just decide for yourself. There's no right or wrong answer. Do you think rolling the dice 100 times and getting 15 instances of a sum of 7 is fairly accurate to the true probability, which we'll calculate here in just a minute? So just think about how accurate you think that is. Pretty accurate, not so accurate. Just kind of think about that. So here's another example of empirical probability. This is when we can't know the true probability. The only option we have is empirical. So for this one, we took a survey and we tried to ask people how they get to work. Do they drive alone? Do they carpool? Do they use public transportation? Do they walk? Are there other means that they use? Or do they work from home? So we went out, we took a survey, we counted up the frequency of each option, and now we're going to calculate the probability of each one based on this empirical probability. I believe there are 200 in the sample, but let's make sure. I believe there was 200 people surveyed. So 153 plus 22 plus 10 plus 5 plus 3 plus 7. So we just want to get that total of how many were surveyed. So a total of 200. So to get the probability, it's kind of the same as getting relative frequency. If you remember that back from chapter 2. So 153 out of 200 gives us a relative probability of 0.765. That's our relative frequency, which we call probability. And we'll continue this for each outcome. 22 out of 200 is 0.11. 10 out of 200 is 0.05. 5 out of 200 is 0.025. So I'm dividing each desired outcome by the total. Other means was 3 out of 200. I had a coworker that skateboarded to work, so I guess he would be considered other means. And then the last one, working from home, 0.035. So you have all these relative frequencies, 0.765 and on down. If I were to add all those together, they should always sum to 1. So all your outcomes, relative frequencies, always sum to 1. And that 1 represents 100%. That's very important in statistics, that all our possibilities added together is always 100%, not more, not less. So using this gathered data, using the empirical method, what is the probability that someone carpools to work? And that would be 0.11, which we could say 11 out of 100, which we could also say 11%. Several different ways to say the same thing. So there's an 11% chance that someone carpools to work. And another question, in a sample of 1,000 people, how many would you expect to use public transportation based on this experiment? So we know there's a 5% chance that someone uses public transportation. If we had 1,000 people in our sample and we multiplied by 0.05, so that's n times p, that gives us an expected value. So we have 1,000 people, we expect 5% of them to use public transportation, and that gives us a total of 50 people. So if I'm trying to budget how many people are going to use public transportation, I can use my gathered data, even though it was sampled only out of 200. Getting the relative frequency allows me to extend my results to a sample of 1,000. So it's really nice to get these relative frequencies, and we can use those to make predictions of how much you would expect with different sample sizes. So again, this is just kind of starting the ball rolling on taking a gathered sample data and extending it to a population or to a larger sample. So that's the empirical method. Sometimes it just involves running a probability experiment on your own. Sometimes it's gathering data and using that gathered data to make predictions. This is often how the empirical probability is used. If I were to go sample 200 other people, these results would be different. So again, that's constantly changing with the empirical probability. All right, the classical method, which is something you've probably seen before, the classical method or approach. This only works for events with equally likely outcomes. So each outcome has to have the same probability of occurring. So this is a little limited. We can't do this for everything. But we can do this for some kind of basic probability experiments. So this is not based on an experiment or sample. It's based on what we call counting techniques. And so you're thinking about how many different ways can something occur. So the probability of the event for the classical approach is the number of ways the event can occur, which they call m, divided by the number of possible outcomes, lowercase n for sample size. And that's also on your formula sheet. The classical probability, the number of ways something can occur. They use a little bit of a different notation here, but it's the same idea. Divided by the number of possible outcomes, so the number in the sample space. So the number in the event you want and the number in your sample space. Slightly different notation, but same idea. Alright, so the same experiment that the casino manager did, now we're going to actually count up how many possible ways these things can occur. So a pair of fair dice is rolled. How many different outcomes are possible? So total number of possible outcomes. So kind of think about that. Think about each die has 6 sides, and each side could land on equally likely. And with 2 different dice, rolling a 5 on one and a 1 on the other is different than the other way around. So these 2 dice are green and yellow. So a yellow 1 and a green 5 is different, where to go, than a yellow 5 and a green 1. So those are 2 different outcomes. So we have 6 different ways the yellow one can occur, and the green one can just be on 1. And then each different way, there's 6 more and 6 more. So it's 6 times 6. 6 of these and 6 of these multiplied together to give you a total of 36 possible outcomes. That's our sample. Well, it's not really a sample space. The newer edition of the textbook calls this N of S, the number in our sample space. Now we want to think about what is the probability of rolling a sum of 7. First we need to think about how many different ways the sum of 7 can occur. So let's think about the yellow die and the green die. So to get a sum of 7, if the yellow lands on 1, the green would have to land on 6. If the yellow landed on 2, the green would have to land on 5 to get that sum of 7. If the yellow landed on 3, the green would have to land on 4. And then all the other ways this could happen. So the yellow could land on 4, the green could land on 3. The yellow could land on 5, the green could land on 2. The yellow could land on 6, the green could land on 1. So I believe those are all the different ways a sum of 7 can occur with 2 dice. So that is 1, 2, 3, 4, 5, 6 different ways out of 36 possible options. So if I do 6, divided by 36, that's 0.16 repeating. So 0.166, I'm going to round that to 7, which is about 17% if we round. So the casino manager's guess, if we go back to page 2, was about 15% when he rolled 100 times. The true percentage is 17%. So I'd say those two are pretty close. So rolling that die 100 times and getting 15 outcomes of sum of 7, pretty close to the true probability of 17%. Let's do this for a different outcome. What is the probability of rolling what they call snake eyes? So snake eyes is both the dice land on 1. And there's only one way for this to happen. Switching them, it doesn't. There's only one way for them to both land on 1. So it's 1 out of those 36 possible. And I think snake eyes wins a lot of money. So I think if it lands on snake eyes, whoever's bet on snake eyes wins. I think it's 36 times their money. So that's a lot. So you can win a lot if you land on snake eyes. I think you get, like I said, 36 times your money. But because there's only a 1 in 36 chance, it's only about a 3% chance of occurring, which is an unusual event. So the casino is willing to give you 36 times your money because they know the chances of it happening are so low and that over time they're going to win 35 out of 36 times. So they'll make plenty of money even if the player wins every now and then. So empirical versus classical. Most of the time these yield similar, but not exactly the same results. So similar, but not the same results. So we kind of saw the empirical approach, we got about 15%, the classical approach, we got 17%. So they're close, but not the same. The larger the sample is for the experiment using the empirical method. So the more times you can gather data. So if that casino manager rolled it 500 times instead of 100 times, the larger and larger sample you get, the closer, this should say it, sorry about the typo, it will be to the true probability. So the larger the sample for the empirical method, the closer it will be to the classical method. This is another demonstration of the law of large numbers. Now the textbook gets into other ways to compute probabilities. You can read this on your own. I don't think this is part of your homework at all. It talks a little bit about simulation and subjective probability. Simulation is pretty interesting. If you take another statistics course, it's a good topic to study. I think I'm going to stop there. I think that finishes 5.1, and then we'll get into 5.2 in the next video.